So today I want to show you the difference between bonding electrons and non-bond electrons. The main thing is non-bond electrons take up more space. Bond electrons are in between two nuclei, and so they're relatively fixed, so they don't take up as much space as non-bonded electrons. Trying to make sure you can see the screen here. So this right here is actually going to be carbon dioxide. And so I kind of made a couple models. I made one. Let's take a look at this. I have carbon in the middle and then two oxygens. Now, it doesn't make a difference if it's double bonds or not. It's just two bonding directions. And then notice the central atom doesn't have any non-bond electrons on it. If it does, it's going to change it up. And we'll see that with the sulfur dioxide. So again, that's linear. And I made a couple balloons. And these balloons are kind of good because they represent the fact that these are electrons within these areas. And it's like overlap of electrons that causes bond and stuff. We'll talk more about that in class. But this will be carbon, and this will be the two oxygens, and they take up space, but notice these two are about the same size, and it'll be linear. So this will be carbon and two oxygens on the end. Now I'm going to change this up a bit, in which now, try to see if that looks better, in which I'm going to look at sulfur dioxide, in which I have a non-bond pair of electrons on top of the sulfur. Non-bond takes up more space. It's going to change this shape, even though carbon has this like sulfur and be the two oxygens. It's going to change it up because of a non-bond pair of electrons. So let me go ahead and grab that orbital, put it together, and then show you what goes on. So that yellow is a non-bond pair of electrons. And notice it's much bigger because it's just on sulfur. It's not contained in between two nuclei. And it causes this, really, to have this bend shape. So you can kind of ignore the yellow in terms of the shape. It goes down. The two pinks are the ones that determine the shape. So sulfur dioxide will be a bend shape because non-bond pair of electrons take up more space and kind of press down. Almost always, if you have non-bond pair of electrons, you can call it a polar molecule. We'll talk about polar and non-polar in class, but just notice that non-bond takes up more space and gives it these characteristic molecular geometries for these various molecules. So to kind of finish this up, I want to look at, this is methane, CH4. That's a classic tetrahedral shape. So this will be the carbon in the middle, and then these will be the bonds to the four hydrogens. These are all the same, so you can ignore the colors. It doesn't make a difference in this case. And so this is a nice tetrahedral arrangement. And so it's going to look something like this. I think I always bring this model. That's carbon in the middle, and then the whites are the hydrogens. So it's a tetrahedral arrangement. Now I'm going to change it up, in which if I look at ammonia, I have a non-bond pair of electrons. So I'm going to replace one of these bonds with non-bond pair of electrons. That takes up more space. It's going to change the shape. So let me give you a second. So I went ahead and made this. And again, the yellow is a non-bond pair of electrons. It kind of makes this pressed out. It takes up some more space. And you have this what they call a trigonopyramidal structure. Let me write that down there. And so notice the difference between this and something like this, in which I made, in which all four bonds were the same. So basically, the take-home message is, note a non-bond pair of electrons, that'd be the yellow, takes up more space and causes stuff to kind of bend. Again, in most cases, if the central atom has non-bond pair of electrons, it's going to be polar.